For the problem 1, the first one is the Poisson process. It is defined by the following, which is the probability of n t1 t2, which means there are k events happened in the time interval between t1 and t2. And the distribution is this function. And it's with the parameter of lambda and t, and we have the following that if the interval t1, t2, and t3, t4 are non-overlapping, then the random variables of n t1, t2, and if it's changed to t3, t4, it's also independent. And the first order probability mass function of Poisson process is first order probability of mass. It is equals to just the same formula of stated above. And the mean, we have it is equals to lambda t, which is a linear dependent of the time t. And the auto correlation RT1 T2 is equals to the expectation of xt1 times xt2, and after derivation we got it equals to lambda the power of 2 times t1 t2 plus lambda times the minimal of t1 and t2. And the auto covariance ct1 t2 is equals to expectation of xt1 minus the mean times the expectation of t2 minus the mean at t2. And we got it is equals to lambda times the minimal of t1 and t2. So here is the property of the Poisson process. And let me make it smaller. And for the second one is the Poisson increasement. It is defined as x of t plus eta minus xt divided by eta, where xt is the Poisson process. And the first order probability of mass is equals to the probability of yt equals to n divided by eta is equals to e the power of minus lambda times eta times lambda times eta the power of n divided by n the permutation. And with that, we have the mean of the Poisson increasement process is just equals to lambda, and we have the autocorrelation T1 T2 is equals to lambda the power of 2 if the difference of T1 and T2 is greater than eta, and it is equal to lambda power of 2 plus lambda divided by eta minus lambda times the difference of T1 and T2 divided by eta to the power of 2 if the difference of T1 and T2 is smaller than eta. And the autocovariance it is equals to 0 if the difference of T1 and T2 is greater than eta, and it is equal to lambda divided by eta minus lambda times the difference of T1 and T2 divided by eta the power of 2 if the difference of T1 and T2 is smaller than eta. This is for the Poisson increasement process. And for the third one is the Poisson impulse. It is denoted as ZT, and ZT is divided as the derivative of xt, where xt is a Poisson process. It is all the derivation from the normal Poisson the original Poisson process, and it has no definition of the probability mass function. And the mean is also equals to lambda. The autocorrelation T1 T2 is equals to the lambda power of 2 plus lambda times the impulse given at T1 minus T2, and the autocovariance T1 T2 is given by lambda times the impulse given at T1 minus T2. This is for the Poisson impulse. So we have the first three derived illustrated of the Poisson process, the Poisson increasement process, and the Poisson impulse process. And for the fourth one, it is the semi-random telegraph signal xt. The semi-random telegraph signal is based on the Poisson points. So we have the probability mass function. It is equals to the probability of at T1 and T2 times interval there are k signals come. It equals to the e the power of lambda t times lambda t the power of k divided by k's permutation. It is just the Poisson formula, and we have xt is equals to 1 when k is even, in the time interval 0 and t, and we have x equals to minus 1, 1 k is odd in the interval 0 and t. So based on that, we have the first order probability of mass function. It is equals to 1xt is equals to 1. It equals to e the power of minus lambda t times e the power of lambda t plus e the power of minus lambda t. It is also equals to, using the triangular representation we have, it equals to e the power of minus lambda t times cosine h lambda t. And we have the probability equals to minus 1, which is just 1 minus the above probability. And it equals to e the power of lambda t times e the power of lambda t minus e the power of minus lambda t. And it is also equals to e the power of lambda t times some sine h lambda t. And it is the first order probability mass function of the semi-random telegraph signal. It is also based on the Poisson points. And we have the mean, which is e the power of minus 2 lambda t. And we have the autocorrelation. RT1, T2, it is equals to the expectation of xt1 times xt2, where it is equals to the value of 1 times the probability of xt equals to 1 plus the value of minus 1 times the probability of xt equals to minus 1. And we just plug in the first order probability of mass function we have just derived above. We get the autocorrelation is equals to e the power of minus 2 lambda times t1 minus t2. This is 1 t1 greater than t2. So when t1 is minus than t2, is smaller than t2, we have it's equals to e the power of minus lambda times t2 minus t1. This is for the other case. So we have for general case, the autocorrelation is equals to the e the power of minus lambda times the difference of t1 and t2 is the absolute value of t1 minus t2. And for the autocovariance, c t1 t2, it is equals to the autocorrelation of t1 and t2 minus the mean value at t1 times the mean value at t2. It is equals to e the power of 2 lambda times t1 minus t2's absolute value minus e the power of minus 2 lambda times t1 plus t2. So this is for the first problem, which is the semi-random telegraph signal. And for the fifth one, it is the random telegraph signal. So we define the random telegraph signal yt is equals to a times xt, where a is a random variable independent of xt. And since a can only take a value of 1 and minus 1, we have the probability of a equals to 1 equals to the probability of a equals to minus 1 equals to 0.5. And xt here is the semi-random telegraph signal. And the first order probability mass function is equals to when the probability of yt equals to 1, we can just substitute yt as a times xt. It is equals to, because a is independent of x, so we can take a outer the loop. And the combination of a times xt equals to 1 equals to, they have two cases. One is a equals to 1 and xt equals to 1. And another is a equals to minus 1 and xt equals to minus 1. And we have, because as I said before, a is independent of x, we can take a outside, becomes two probabilities. It equals to the probability of a equals to 1 times the probability of xt equals 1 plus the probability of a equals to minus 1 times the probability of xt equals to minus 1, and it is equals to 0.5. And the probability of yt equals to minus 1 is just 1 minus the above probability, which is also 0.5. Yeah, sorry. And for the mean of yt, we also substitute it as a and x times xt. And because the mean value of a is 0, so we got the mean value of yt is 0 also. And for the autocorrelation, T1, T2, it equals to the expectation of a to the power of 2 times xt1 times xt2. And we can separate a outside. And since a follows is a random variable, so the expectation value of a to the power of 2 is equals to 1. So it is equals to e to the power of minus 2 lambda times the difference absolute value of t1 minus t2. And for the autocovariance, C T1 T2, it equals to the autocorrelation R T1 T2 minus the multiplication of mean value at T1 and at T2. Since the mean value is 0, so we have the autocorrelation is equals to the autocovariance in this case. And this is for the fifth problem of random telegraph signal. And for the sixth part, it is random walk. So random walk is defined as, for example, we toss a fair coin for n times with k times heads and n minus k tail, and we increase it by 1 if we get heads, and we decrease it by 1 if we get tail. So we have the first order probability mass function is, so based on this we have xnt equals to k times s minus n minus k times s, as I said before, and it is equals to 2k minus n times s. So we have the first order PMF equals to the probability of xt is xnt, because we have n trials, equals to 2k minus n times s equals to rs. So we have the probability of k equals to, because we solve this equation, we get our k is equals to n plus r divided by 2. It equals to this one. And we have our mean value, it is equals to 0, because it's by common sense. If we just randomly walk, and we will end up being at 0. And we have the autocorrelation. It is equals to the r t1 t2. It is equals to expectation of x. We represent t1 as mt, represent t2 as nt, and it is equals to the minimum of m and n times the power of it, s the power of 2. And the autocovariance C T1 T2 is equals to the autocorrelation, because the mean value of random walk is 0. So the autocovariance is also equals to minimum value of n and m times s the power of 2. So this is for random walk. And for the last one, it's the Wiener process. We just make the random walk smaller. The Wiener process is a limiting process of the random walk. We define it as if we take the limitation of random walk xt. And since we know that the second moment of the Wiener process should be finite and non-zero, so we have the limitation of constraint of the limitation of x approaching 0, n approaching infinity, and s the power of 2 divided by t approaching alpha, where alpha is a constant. To derive the first order probability of mass, we first calculate the first order density function. P, WT is smaller than W, is equals to the limitation of P xt smaller than W, and we just plug in NT because we have done N trials, and it equals to this formula. It is the density function. So we from the first order. Oh, no, this is not the density function. It's not the distribution function. Yes. The density function is just the derivative of the distribution function. So we just take the derivative of the above formula. And we get it is equals to this formula. And so because the mean value of the random walk is 0, so the mean value of the winner process is also 0, since it just take the limitation of random walk. Sorry, this should be W. And the autocorrelation of T1 and T2, we just plug in the limitation plus the autocorrelation we derived for the winner process, and it is equals to alpha times the minimum of T1 and T2. And for the autocovariance, it is also equals to the autocorrelation because the mean value of the winner process is 0. So this is for the winner process. So this is for the problem 1. We have say all the 7 process.